Hello, grade 11s. Oh man, I'm excited for this term. I think we're gonna go into it well structured. We're just gonna continue our good work ethic from term one. Okay, so this first video is just kind of a recap of some of the principles related to functions and some of the terminology. So if we look at this worksheet, which is on the website, and it's going to automatically update as we work through it, so it's hopefully a bit more accessible. So with functions, let's just look at some of the relations, some of the principles. Then we're going to look at horizontal shifts. That's going to be the next video. And then from there, we're going to move on. So to start with, let's just look at this function, which I'm calling f of x. And I'm going to say that f of x is going to be equal to table mountain. There it is. No specific, not x squared plus whatever. Just this function that we've got, which is table mountain. And we can see it over here. Here it is going along. And we're just going to look at the intercepts. What are the intercepts again? So as you're going along, just think, oh, what are these different bits of terminology? Well, intercepts, let's see. Can you see where's the y-intercept? There it is sitting over there. I see it right there. And we don't know much about this, except we know one crucial bit of information. What is that? Well, if we write down the coordinates, yeah, at that point the x value is 0. Don't know what the y value is, we haven't been given it, but we know that the x value is 0. So if we wanted to find the x-intercept, we'd just put f of 0 in and we'd do it. So if we got x squared plus 7x or something, we'd replace all the x's with 0. Okay, then we've got some y-intercepts. I mean, at least we've seen the y-intercept, at least some x-intercepts. Where are the x-intercepts? I see one over there going along. I see another one there. I see another one there and another one there. What do we know about x-intercepts? Well, if we write down the coordinates of all of these, then we'd know that the y value is 0. So we'd know that about all of those x-intercepts. So if f of x equals table mountain, f of x is our y value. So we'd know that 0 equals, and that would be able to help us get, and I don't know why I keep doing these the wrong way around, that's going to give us our x-ints, and an f of 0 will give us our y-intercept. Okay, so let's keep going along. And if you're drawing this, you don't have to get this table mountain function perfect, just some rough sketch is fine. Okay, so, and you pause the video as you go along. Domain and range. Domain. What does domain have to do with? I can hear you going, domain, well, yep, x values. Okay, so our domain has to do with all the x values that are valid inputs. So where do our x? Let's say that this thing starts over here and it ends over there. So this would be our domain over here. There's our domain. And just remember to use square brackets when we're including and use round brackets if we're excluding. So if we're including this point or if this one were excluded, then just remember those brackets. And the range, well, the range has to do with the y value. So let's see, here's the smallest y value, looks like it's down here, and the biggest y value should be at McClear's Beacon, I think, but I think on this version it's over there somewhere by the cable car. So this is our range to do with our y values. And again, remember to use these square and open brackets. So let's just get that down here. Our range has to do with the y values. Cool. Just recapping so far. Now what happens if we had our table mountain function, and I said that we've got table mountain, so this was f of x equals table mountain, and we considered another function that was, let's call this one g of x, and say if g of x is just twice as big as table mountain, what would it look like? And I guess let's do that, and so our notes look good afterwards. We'll make it blue, although that's a terrible blue, isn't it? Anyway, so it's going to be that blue to match it. So if g of x is 2 times table mountain, Well, there's twice as big. You can see here's the idea that it's going to be twice as big. But it's not going to look like that. That looks like it's twice as big. Why not? Why? It looks like it's twice as big. Let's look at some points. Look at our y-intercept. It's about 1 mouse cursor high. This one here now is 1, 2, 3. So it looks like we've multiplied it by 3. That doesn't make sense. The bottom's at the bottom and the top's up by 3. But we said it's twice as big, and this is definitely twice as big, this picture that I've added here. Okay, what about the X-intercepts? If this X-intercept is 0, the Y value is 0. So the f of x is 0. And g of x is going to be twice as big. Well, surely 2 times 0 is still 0. So that x-intercept here shouldn't have changed. So if we go for this and go, well, the y-intercept should be twice as high, so it should be about 2 mouse cursors up and be up here, and the x-intercept should stay the same, then that looks a bit more reasonable. There it is, x-intercepts are the same. It's just a crucial point to note that when we're multiplying it by 2, we're stretching it out from the x-axis. So all these x-intercepts stay the same. This y value is increased by 2, and if we look here, this point down here was at a negative value. Let's say it was minus 3, and it would be twice as big, would be at minus 6. So everything stretches out from the x-axis, and that's going to be really helpful when we get to trig functions. Okay, I know that we're flying, but we're flying because we're just recapping to get into what we want to do this year. So this is just quick stuff. You're going to be doing some work in parabolas and plenty of stuff, so don't worry. Okay, let's see what happens if you multiply it by a negative. So, and I've said by a because, you know, you've got y equals ax squared plus q, y equals a over x, those, and we're going to come back to those general forms, but that's why we're multiplying by a. So what happens if we're multiplying by a negative? Well, we're going to take that whole graph, and if this were positive, let's say that was positive 3, well, it must move down to be negative 3. Let's look at our x-intercepts. If this was 0, well, the y value is 0. What's negative 0? Still 0. So again, I could ask a similar question to say, well, it's not going to be that, because that doesn't make sense. If that's 3, that's not negative 3. Again, it was about 1 mouse cursor, 1, it should be over there. If that's 0, the y value, f of x, then negative 0 is still 0. So the negative is, again, it's a reflection about the x-axis. So let's draw it like that. There, that looks like, it's like we've put a mirror on the x-axis. So let's capture our thinking there to say that f of x has remained, it's still our lovely table mountain function. But this function now, h of x, is negative table mountain. In other words, it's just taken it and it's reflected about the x-axis. Let's just capture that here as well to say, so this is a reflection about the x-axis. So if the question, if somebody asks you, well, reflect this function about the x-axis, all it means is take everything, make it negative. Okay, let's just pause for a second, and we've gone right to the end here. So we've only got one more thing to do. Whew, take a breather. How are we looking? I hope that you've been pausing the video as we go along. It's running through quite quickly, but that's because we, as I said, we're recapping and we're pausing and getting back into the term. And let's just pause. Okay. So, ready to continue. Let's get back. What happens if we add a constant? And we add the constant q. That's because we normally talk about ax plus q, or ax squared plus q. So we've got our table mountain function. Here it is. And we've got a few spares, so let's give ourselves a chance here and say, well, f of x is still our beloved table mountain. Okay. Now we're going to take a green function and we're going to say this one here, j of x. We're going to take Table Mountain and we're going to add another 10 to it. In other words, we're going to take Table Mountain, which was f of x, and we're going to add 10. And this is notation that we need to be comfortable with. We've taken this and we've added 10. What would the new function look like? So we've taken Table Mountain, there it is, and we've added 10. So we've just added 10. We don't have a scale, I don't know what was what. I said that was about 3. If we keep with that, then it will be up there somewhere. But it's just translated or shifted up by 10. Let's say that we've got another function and we've got this bright blue, and k of x, our new function, is f of x, so it's Table Mountain, and this time we're going to subtract 10. So we're going to take Table Mountain, take our original function, f of x, could have been a parabola, could have been a hyperbola, could have been an exponential, a straight line. We're going to take that function and we're going to subtract 10. So we're just going to move it down by 10. So I'm guessing it's going to be about there. But the point is, if we add a constant, obviously if we add a positive, it's going to go up. And if we add a negative, it's going to go down. Okay, so let's head into the last bit of this video. And I know, sure, term 2 is hitting us. Okay, so last bit, and I can imagine some of you saying it's just carrying on. Yeah, that is it. That's maths. We just keep going. So let's finish it off, and I'm going to go through this one a bit more slowly. We've got our original function. F of x equals Table Mountain. It's been drawn for us. There it's sitting pretty. And I'm going to consider a new function. Our new function we want to draw is, that blue really looks like it. I'm going to do black, and it's going to match with the blue graph. And we're on, let's say, m of x equals, let's call it p. P of x, I'm sorry to change my mind, I just know that we keep some of the letters for certain things. So like p is going to be our horizontal shift. So let's go back to m of x, because we're not going to use that. It could be gradient, but that's fine. M of x equals Table Mountain, which was f of x. If it were the case, then it would just be the same. We're going to multiply it by 2. So multiplying by 2, we're already thinking we're going to stretch it. In fact, let's multiply it by -2. Okay, we're doing two things. We're stretching it out and we're reflecting it. And then how about we add 10 again? Okay, so that's our new function. And what I want to work through is just our thinking of what this function would look like. So we've got the negative. So we can take our negative and say the negative means that we're going to reflect it. There it is, perfect reflection about the x-axis. We're also going to multiply it by 2. So we're going to take that reflection and we're going to multiply it by 2. There we go, the x-intercepts line up. If this were 3, this would be -6. This is 0, it's still 0. If this bit here is also 3, that's -3. If that were 2, that's -2. -4, because we multiplied by 2 as well. Okay, and then we need to add 10. So we're going to take that. We've done the negative. That's the reflection. We've stretched it out by 2. And we've moved it up by 10. So that graph would just be sitting over there somewhere, give or take. We don't have a good scale. But it's a good process just to have thought through. What is each of these things doing? The negative, reflecting. The 2, stretching it by 2, but from the x-axis each way. And the 10, moving the whole thing up by 10. Okay, so that's recap of things we did. And when you did it last year, it happened to be a parabola that you stretched out and moved up and down. Or it was a hyperbola and you went, oh no, it's in the first and the fourth quadrant and first and third quadrant, and then you moved it around, or you had the exponential and the exponential move, but the concepts apply to all of them the same way. So what we're going to move on to in the next part is a horizontal translational shift. And there's nothing to draw here because we're going to do this with the parabola. And this is just, how do we move this function left and right? The moment we've stretched it, we've reflected it, we've moved it up and down, but last year we never moved it left and right. How would we if we had a parabola and we wanted to draw the parabola down here? Or if we wanted to draw it further right in the positive direction? How do we move things left and right? Well, come back for more because that's what we're doing next. So, yeah, that's our recap. Well done. This is term 2 hitting us. I like it.